Welcome everybody, thank you for joining. Glad you could be here. Grab yourself a notebook, a pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you out of nowhere. Today we have a problem from the 2006 AP Calculus BC exam. So you can give this a look, try this problem for yourself. Give yourself about 12 to 15 minutes. If you're in AB calculus, sorry, but parts C and D are pretty much off limits for you. When you're ready, you can join back and see how we do it here. All right, let's get started. So consider this differential equation. All right, it has x and it has y in it. As long as y does not equal 2, let f of x be the particular solution to the differential equation with the initial condition given. So when x is -1, the y is -4. That's important. And let's look at part A. Part A says evaluate dy dx and d squared y dx squared. So that's the second derivative. All right, so we're going to have a little bit of work here. At these points, x is equal to -1, y is equal to -4. So first let's just figure out what dy dx is here. So dy dx evaluated when x equals -1, y equals -4. We're basically just going to plug in -1 for x and -4 for y. So we get 5 minus 6 over -6, which is just 5 plus 1. That is 6. Now, for d squared y dx squared, we're going to have to take the derivative of dy dx. So let's first rewrite it in a slightly better way. 5x squared minus 6 times the quantity y minus 2 to the -1. Amazing. And that's our dy dx. That looks like a g. So in order to find the second derivative, we're just going to follow the power rule here. Then we're going to use the chain rule, plus 6 y minus 2 to the -2 power, and then times dy dx. That is our second derivative. Since we're plugging in the same point, we can use -1 for the x, and we can use -4 for the y. Let's put that on bottom again. So this is -6 squared now, and this is multiplied by dy dx, which we just evaluated was +6. Okay, so this is going to leave us with -10 plus 36 over 36, essentially, which is just -10 plus 1, or -9. So there's our second derivative. There's our first derivative. Pretty straightforward. If you're in BC calculus, this should be very comfortable. Pretty smooth. Just taking derivatives, plugging stuff in. Part B. Is it possible, interesting, that's going to be how we answer the question, is it possible for the x-axis to be tangent to the graph at some point? Okay, well, let's think about what it means for the x-axis to be tangent. Tangent means it touches the curve. The x-axis touches the curve, which means that y equals 0. So it's first asking, is y equals 0 on the curve? But it's also asking if it's tangent, so it's also asking if y prime is 0 at that point. So first we have to establish whether or not it even touches the x-axis. Oh, and y would also equal 0. Okay, so let's look at dy dx then. dy dx would have to be 5x squared, whatever the x value is, minus 6 over 0 minus 2, you understand? So that's going to be presuming that the y value is also 0, which it would have to be in order to be touching the x-axis. So we basically have 5x squared plus 3. And that's never going to equal 0. In fact, that's always going to be greater than 0. So therefore we have, it will never be tangent. Doesn't mean that it won't cross the x-axis, it just won't be tangent to the x-axis. Because if the slope never goes flat, well then we're never going to have the same slope as the x-axis. Or rather, I should say, if the slope doesn't go flat when it crosses the x-axis, then it can't be tangent to it. Okay, so kind of interesting discussion on that one. Part C is where we got to do some work. Find the second degree, it's not that big, Taylor polynomial for f about the point x equals -1. So a reminder that the Taylor polynomial, especially if we're doing T2, which is the 2 refers to the degree. T2 of x centered at -1. It's going to look like this. It's going to be f of -1 plus f prime at -1 times x minus -1. In other words, x plus 1. Plus f double prime at -1 times x minus -1 squared, but we can't forget to divide that by 2 factorial, and technically t to the n x would just continue, and it would be nth derivative. Or would it be the nth derivative? The nth term, it would be the n minus 1 derivative, I guess, at -1 times x minus 1. X minus -1. I think you get the idea here. To the n minus 1 over n minus 1 factorial. Yeah. So kind of wild there. We only need the second degree portions, which we have most of the information of this on, don't we? We have that. We have that. We even have that. We calculated those in part A. So this is -4 plus 6 times x plus 1, plus, I think this one was a -9, was it not? Yeah, there it is. -9 over 2 factorial, which is just 2, times x plus 1 squared. So -4, I mean, you could work this out, but you really don't have to. I think it's fine to leave it in this format. In fact, it kind of shows that you realize this was relative to the factor x plus 1. So that's our Taylor polynomial. It really wasn't that bad because we already did the derivative at and the second derivative at the point x equals -1. So really not too bad there. Now part D, once you're worn out, part D is going to ask of more. Using Euler's method, use Euler's method to approximate f of 0. Show the work that leads to your answer. So what Euler's method is using the tangent line, but then kind of adjusting the tangent line as we go. And we're going to do that in 2 steps. So we start off at x equals -1. Let's visualize what's going to happen here. We have x equals -1, y equals -4. Let's call it like right there or whatever. I don't know what this curve looks like, but I know that the slope there is 6. So it's sort of heading like upwards pretty steeply. However, I know it's not going to continue going at that same slope. It's going to be changing its slope. So what Euler's method does is it's going to get us a little bit closer, but then at that point, I'm going to adjust my slope. I'm going to stop going along that tangent line because it's going to start deviating. and I'm going to steer the function, I'm going to steer the tangent line according to the slope at this new x value. And maybe that will either flatten it out, or maybe that will make it even steeper. We'll have to see. So we start off with the tangent line at the point -1, -4. That's going to look like this. Y plus 4 equals the slope at -1, which was 6, x minus -1, or x plus 1. Now what we're going to do is we're going to estimate f of 0.5, sorry, f of -0.5. And we're going to do that by going forward and using this tangent line. This is going to be approximately 6 times -0.5 plus 1 minus 4, which is equal to half of 6 minus 4, -1. So this tangent line so far is going to take us to -1. Then from there we have to find what the new slope would be. So we have to find dy dx at this new point where we have x is -0.5 and y is -1. So that's going to be equal to 5x squared. I think it was minus 6 over y minus 2. So this is -1 minus 2. 5 over 4 there, basically. And this is going to be a -6 over a -3, which is a plus 2. So 5/4 plus 2. Or we can call this, I guess we can call this 13 over 4. Now this is the new slope when x equals -0.5 and y is -1. This might not be on the curve, but it's close to the curve. So we're going to use this slope now. It kind of flattens out a little bit to about, that's 3.25. And now we're going to use that to get us to x equals 0. So we could say that the equation of this tangent line is something like y plus 1 equals 13 over 4, x plus 0.5. So we're going to approximate f of 0 by saying f of 0 is approximately 13 over 4, 0 plus 0.5, and then minus 1. And this is simply 13 over 4 times a half, 0.5 just 1/2, minus 1. So we have 13 over 8 minus 1, which is 8 over 8. And so we have 5 over 8. That means that f0 is approximately 5/8, or 0.625 if you like decimals. So this was a way of using Euler's method to approximate where the function would actually be at. It's possible that the function doesn't really do that. It's possible that the function is like up there, or maybe it flattens out sooner. Who knows? It just tells us to approximate what f of 0 is. So that is our approximation. It doesn't ask us to truly predict what the curve is going to be at. Alright, so this was an example of using some BC techniques to write both a Taylor polynomial and to apply Euler's method for approximating a function value, which is sort of like using a tangent line, but sort of re-steering the tangent line every so often, a couple times along the way, in this case, two times. And they gave us a differential equation in the first place, which had us do some implicit differentiation. So yeah, this problem was quite thorough in terms of the techniques it makes you use. It has you dip into some integral ideas as well as some derivative ideas. Okay, that's enough blab out of me. Hope you learned something today. See you guys next time in the void.